Thanks for the introduction. Again, I'm Andre Perkins, University of Washington, working with Greg. And as he said, we've been pushing the frontiers of what we can do with LMR, and especially with respect to what we know as online data assimilation. So, of course, the broader picture here is the LMR. We're looking to provide, the best damn reconstruction we possibly can. We want to have fully physically consistent spatial fields, but also we want to have those spatial fields and how they evolve in time correct. Luckily, with DA, you get some of this in the model. And for our very first results, the LMR version 1, which was in the 2016 paper, they were really good. When we validated against the instrumental record, everything came out, it worked. It was kind of amazing for kind of a first pass at what we were doing with this. And everything I'm comparing in this presentation is going to be against version 1 results. You saw a lot of updates by Robert, but I'm not comparing to those yet. I hope to in the future. So LMR 1 was good, but there's one thing that was missing from that with respect to DA, which is common to DA, and that's the use of a forward model. So there's no mechanism to transfer any information at a given point in time to another point in time. The only thing we're using is proxy information. That's the only temporal information we had in version 1. So distilling about 3 years of work on my master's degree into about 4 words, like would adding 1 help? So that's the main question we were coming at. Can we add a model that will improve our reconstruction results? So I'll be talking a bit about the Ensemble Kalman filter. I had some great discussions over lunch. I'm going to share my love data assimilation equations with you. I'll talk about the offline and online assimilation approaches, why most paleo reconstructions have opted for offline methods so far. And so we're using this model called a linear inverse model in this project. So I'll tell you a bit about those, how we incorporated them, show you the results from the paper, and then some future work we're planning on moving forward with these linear inverse models. Okay, so the Kalman filter equation. This is our update equation. I'll go through it step by step. We have our prior ensemble, EXP. This is our first guess estimate of whatever state we're trying to estimate. So it can be your temperature, precipitation, pressure. On the right-hand side, there's a little schematic for a single variable case, where the mean value is your actual estimate and the spread, that Gaussian curve, is your uncertainty around that. And from that prior, we also have our observation, which we want to incorporate into that prior. To do that, we need to estimate an observation from our state. We use that using an operator denoted by H there. We get these estimated observations. That gives us a difference from the observations and the prior, which we know is an innovation. We spread that back into our prior ensemble through the Kalman gain term, which is simply using covariances between your estimated observations and the full field. And then the amount of information you incorporate is then weighted by your uncertainty in both terms. So when you go through this equation, you update, you get an analysis. It has a little less uncertainty than what you started with. It's weighted more heavily towards what you're most certain in. So in the schematic, that would be the prior case. And at the end result, you get this analysis term, which is your best guess, considering your model and your observations. So that's the update in a nutshell. But the one other thing you can do with this is you can consider, okay, I have this new state. How am I going to treat this in time? We know in the climate system that, the previous state has some effect on the following states. The amount of effect depends on how long of a time scale you're looking at. So in the LMR version 1 results, we're using offline assimilation, where we don't think that the assumption there is that there's no effect from the previous times on any following time. So we consider each time independently. So this schematic, you have maybe some ensemble of temperature, some ensemble estimating your temperatures. The little black dots, maybe you would consider observations. But the fact here is that in offline assimilation, you make the same guess for every year. You don't really think that you have any skill from one time to the next. You assimilate that, makes things easier computationally, and you get your best estimate. But there's no information that's considered between these time periods. Now, with online assimilation, which is the more traditional data assimilation approach, instead of using the same prior estimate for each time, we have our initial ensemble, we assimilate some data, and we end up with this analysis. Then you can take each of those ensemble members and use a forecast model that you think is skillful, propagate that forward in time. It'll give you your new ensemble that's maybe a little bit hard to see. Again, a range of possible states, and instead of using the exact same prior for every year, you're now using these forecasted states as your best guess at each time period, and you repeat that process. So in the numerical weather prediction field, this is mostly what's used. And Greg, I completely forgot what the percentage is that you quote all the time. But the idea is that most of your skill at these subsequent time periods is coming from observations that you've assimilated previously in the step. I don't know if you've got it. 85%. I was going to guess 80 plus, but. So that's the main difference between online and offline here, is that we have this forecast model to translate our best guess, as in models, of how these dynamics play in time. So why not online from the start in the paleo data assimilation setting? So for a typical experiment that we're doing in LMR, we have about 100 ensemble members. So that's 100 states. Maybe there are multiple fields. It could be temperature and precipitation. Gridded product, so T42, it's 66 by 44 or something along those lines. Yeah. So you have, say 100 of those state vectors. We are reconstructing for at least 1,000 years, and then potentially also doing 10 to 100 Monte Carlo realizations where we're randomly sampling things. So it's a lot of zeros in there. Now imagine trying to put in as your forecast model a GCM to forecast all of these. Either one, you'll be waiting for a bit of time, or number two, your supervisors might start to question your utilization of resources. So underlying all of this is the fact that when we're looking at annual timescales, climate forecasts don't have that much skill. If we could get a perfect forecast from one year to the next, a lot of problems would be solved. But also, we would be spending the time doing this, right? We would be spending the time forecast. That's not the case. So if you have you consider a climatological spread that you might estimate from observations, most of the times our forecasts are very close to that climatological spread. So there's maybe a little bit of information in the forecast, but you'd either have to use really large ensembles to get at that little tiny bit of information, or maybe you're only waiting for certain climate regimes to show up that are more predictable. Long story short, GCMs are expensive. It's easier to guess with climatology. So that's what we did. That's what most people have done. That's not to say people haven't tried doing online paleo DA work. Some of the earliest stuff, again, coming out of Greg's group, Angie Pendergrass, who I believe is here at NCAR, was working with a quasi-geostrophic model, slab ocean, did some very simple experiments to see how assimilation worked with different time-averaged proxies. The main result relevant to us is that when we are forecasting and getting useful forecasts, we need predictability beyond the resolution of our observations. Another study, Anon et al. In 2012, was looking at how proxy sparsity affected some of these spatial reconstructions. They tried a persistence forecast, and in that case, they found for their spatial fields, no skill was added, and in some cases, it even made it worse than that. So not a successful online approach. And maybe the closest thing to what we were trying to do was Matsakaris et al. In 2015, where they were assimilating decadal scale temperatures from the Pages 2K network, or not decadal, continental scale temperatures from the Pages 2K network into decadal means at continental scales for the 17th century. So they're using a GCM, an MPI variant, where they were doing decadal forecasts for 10 ensemble members to see if the online or offline method had better results. And the figure on the right is some of their temperature reconstructions compared to the black line, which is a proxy estimate for that time. And the main point is that they couldn't discern, there was skill, but there was no discernible skill added over the offline case. So for us, what these previous projects kind of alluded to is that we need sufficient predictability, but also the ability to probably run really large ensembles to get at this low amount of skill that we have in climate forecasts on annual timescales. And then in came our friend, the linear inverse model, which is an empirical model. Means that you can calibrate it or train it on any data source that you have. So it could be observations, could be models. When it comes down to it, you have your climate state X. You represent the time tendency as a linear equation. So you have a linear operator multiplied by the state plus some random white noise. You integrate that. You get a mapping term, G1, which can take any state you have at time t to the next time you're doing, which in our case is annual forecasts. The main point of the story here, we are looking for cheap. This is just a matrix. You only have to do a matrix multiplication to do a forecast in time. Next question, does it have skill? And there's a really cool study by Matt Newman, who I believe is in the audience. Nice to meet you. He was looking at hindcast skill of these linear inverse models at forecasting temperature, surface temperature over the instrumental record on 2 to 5 year and 6 to 9 year timescales. These figures on the right are showing you some of the grid point anomaly correlations for those forecasts over that time period. And so he's comparing the linear inverse model, which is this row right here, first against a persistence forecast, which was sort of the baseline experiment for skill, but also against much more complicated full GCMs and how they could forecast on these timescales. The really kind of crazy thing is that when you look at the limb skill spatially compared to some of these other experiments, it's very similar or better in some of these cases. So that was alluding to the fact that maybe these models are really only capturing some of the linearly predictable modes of climate variability anyways. And if that's all they can do, we can just consider using the limb instead, maybe. In our case, that's the perfect outcome, right? Because then we just have to do matrix multiplication, we get our forecast, it has some skill, we're happy. So this is our forecast model that we ended up going with. Maybe underselling how much work it was to implement this, but so we have our update equation, and then simply we want to take the analysis that comes out of a given year and forecast it using that the mapping term into the next year to use as our prior. The limb calibration we used, we're going to have multiple calibration or multiple data sources we're calibrating on, but we're smooth the data with a 1 year running mean, removed any warming or removed any trends because we don't want those trends to be ingrained into the linear inverse model. We solve for G1 based on lag covariance statistics. And we're using a reduced state space by reducing to 8 leading modes of variability in EOF space, just to simplify some of the calculation. Yeah. Yeah, I'll show that in the next slide. Yep. One other thing we had to do, so the linear inverse model is a damped model, meaning all the forecast modes decay in time. That's not to say that there isn't constructive interference that can lead to some growth in a certain field over time, in the anomaly in a field over time. But because of that damping, we also had to handle the fact that if you get too small variance in your prior ensemble, filter divergence happens, where you throw out all of your observation information essentially because you're too certain in the prior estimate. So we got around that by using a variance adjustment technique where we blend in some extra variance from a static source, and the static source here is climatology. And we just use a simple linear blending term A that goes from 0 to 1, where 1 is we're using all forecast information, and 0 we're using only climatology, which is equivalent to the offline case. So the experiments that we ran for our study, we used 4 calibrations of a linear inverse model that sort of spanned model to purely model to observational space. So we have 2 last millennium simulations from CCSM4 and MPI. We have Berkeley Earth surface temperatures from 1960 to present as our observational record, and 20th century reanalysis is sort of our hybrid model observation calibration. So we're using these calibrations. We're taking the linear dynamics from each of these data sets to use as our forecasts. Additionally, we performed a persistence forecast to test against. The basic reconstruction setup, we're reconstructing 2-meter air temperatures from 1850 to 2000, so that's during the instrumental period. We're using CCSM4 as our prior, so those are annual average climate states as our prior. And then all the proxy system models were calibrated against GISTEMP, and we're using Page's 2K data. We did this standard Monte Carlo resampling as they did in the 2016 paper, which had resampling of proxies. We used 75% of the proxies, and we're drawing 100-member ensembles. And for that tuning term I talked about on the last slide, we were searching in between a value of A equals 0 and A equals 1 for some value in there where our reconstructions were doing better than the offline case. So that's sort of our tuning coefficient. So diving into some results, we start with global mean temperature. The global mean temperature comparisons are done against GISTEMP. Sorry that it's hard to see some of this on this projector. These are global mean temperature. The different colors here are the various limb reconstructions. The dotted line is offline, and the solid black line is GISTEMP. Main point from these is that we do capture very well some of the longer-term low-frequency variations in this. It's maybe hard to notice, but the general interannual variability seems to be a little bit less than the offline case, and I think that ends up helping us out. So because we do Monte Carlo resampling, we also have about 10,000 realizations of global mean temperature that we can then do bootstrap resampling to get some error bounds on our skill metrics. So we're using CE correlation, and then I also show the trend just as an interesting interesting product to note. And for CE, we see these 4 scores of global mean temperature are all the limb estimates. So for these A values, we found CE scores that were well above the offline case. And the persistence case you can see is down here on the bottom. For correlation, it's a little different. Persistence ends up being the best in correlation, and all the limb reconstructions except for the Berkeley Earth end up improving upon the offline case. And then CE, which is heavily dependent on the trend, you see that for the limb reconstructions, the trends are all kind of hovering around the central amount for what GISTEMP thinks is the right trend. Offline is maybe on the upper end, and persistence is completely out to lunch up here. It might be harder to see, but that's part of the reason why the CE score is so low for that one. If I detrend these and look at these skill metrics, on average, the coefficient of efficiency for the detrended global mean temperatures is about 57% better than the offline case for all the online limb reconstructions. So that was a very interesting thing to see. And detrended GMT is more getting at the interannual, how well we're doing with interannual matching. Spatially, some interesting things pop out. So these are delta CE maps, or the change in CE at these grid points compared to the offline case. So we have our 4 linear inverse model calibration reconstructions. The climate model calibrations are on the top. The 20th century calibrations are along the bottom. The first thing that pops up improvement-wise is that all of the limb calibrations seem to be improving the most in the same areas. So we have Western North America, this Barents Sea, into Northern Europe and Central Asia corridor. All seem to be seeing the same improvements in CE. But when you look in other locations, the 2 instrumental calibrations also introduce some serious degradations in spatial skill, unfortunately. which is not the results I was expecting because we are validating against the instrumental record. So I would have, offhand, thought that the calibrations on the instrumental record would have been better. But it just turns out that the climate models turned out to give us some better results. I think I'll skip over this slide now. But the key results for this paper were that, yes, we could improve over the offline case by using some form of online DA reconstruction. And importantly, that the climate model calibrated limbs did well in both the global mean temperature and spatial fields. So the paper goes into much more detail about this. You can find it in Climate of the Past. But we've also published the data and the code that we use to run these reconstructions on there. So moving forward, this was a very, I think, good result in the sense that because climate models turned out to be the best limb calibrations for us, that opens the door for us to calibrate basically an entire climate model if we wanted to in a limb. So anything that we think has reasonable linear dynamics that are connected to something that you can assimilate, either it's related to temperature or precipitation, there's potential that we can use that in a limb forecast to hopefully get some interesting temporal dynamics linked into these reconstructions. So in thinking about which fields have longer memory and might be related to what we're reconstructing, two fields at first popped out as potential ones of interest. First one, ocean heat content. Very short record that we have of upper ocean heat content, even shorter of deeper ocean heat content, although I'm not sure if we would get much information about deeper oceans. And then maybe sea ice. That one's a bit of a stretch potentially just because most of predictability, say in sea ice concentrations or sea ice extent, maybe are on sub-seasonal or sub-annual timescales. But there is like sea ice thickness, which is a potential that we can forecast longer than a year, something that we would need to put out there. So we've done some preliminary predictability experiments with ocean heat content. And so these are somewhat similar to the experiments in Matt Newman's 2013 paper. Essentially, we take CCSM4 last millennium output, calibrate a limb on 700 years of that data, roughly 700 years of that data. It was randomly pulled out. And then see how well we can use that limb to forecast CCSM4 data. So how linearly predictable is the natural variability and forced variability in CCSM4? And so when you do those experiments, we're using 4 variables in our state. We have upper ocean heat content. Sea surface salinity is not a prognostic variable, but it might be interesting for forcing or incorporation because it can be related to some of the proxies we're using. And then zonal and meridional wind stress, which are key components of the variability for ocean heat content. These are grid point correlations, again, of those one-year forecasts. So generally, ocean heat content is red, saying that we have some scale in the up and down of that time series. And then, interestingly, the wind stress, we see the bullseye across the tropics, and then kind of fans out. It gets a little less red as you go up into the mid-latitudes, kind of hinting at potential like teleconnection dynamics that are going on from there. You can compare the linear inverse model forecast, one-year forecast, to the persistence using relative error. So this is a relative mean squared error estimate. Basically, red means you do better than a persistence forecast. Blue is you do worse. Again, the tropics for ocean heat content and sea surface salinity jump out as an area where the limb with associated dynamics, probably ENSO related, do much better than a persistence forecast. And then there's some blotches in subtropics, maybe getting into the storm track, where persistence seemed to be a better estimate. Wind stress, there is no information in persistence forecasts, which is why it's red everywhere. So with that, we plan to hopefully integrate these multivariate limbs into the LMR code and perform some long-term reconstructions with ocean heat content definitely, and hopefully some sea ice fields. There's still a question there of whether or not we're adding dynamical information with a limb, or if we're just doing a variance tuning exercise by looking across these blending coefficients. So coming up with some experiment to test whether some dynamical information, like from the ocean heat content fields, are being imparted on our actual proxy reconstruction will be useful. And then also potentially investigating forcing. I know Julian will be talking a little bit about that maybe, but not this kind of forcing, but we've talked about that. So moving forward, there's a lot of cool things that are coming up. I'd like to thank NSF NOAA. I'd like to thank Greg and Robert especially for all their help with this work, and Matt Newman for the initial email correspondence and how to set up a limb. So I'll end it there. Be happy to take some questions.